A black hole is a object that is so dense and so massive that it creates a region in space from which light cannot escape. That is, the escape velocity of an object from that point is faster than the speed of light. And since, of course, no speed faster than the speed of light is possible for objects that have mass, you cannot escape from a black hole, unless you're lucky. That's what Stephen Hawking actually came up with, right? So let's look at some of the math of it. The math of this is actually fairly mundane, but the concepts, of course, that it provokes are not mundane, right? So let's imagine that we've got a singularity, a black hole like this, right? And one of the problems with singularities is that it creates discontinuities, infinite curvature of space. And so general relativity doesn't really work. We really need to get a quantum model of gravity, and because general relativity develops these infinities that it really can't get around, whereas quantum mechanics gets around that by possibly not being infinite, right? it's probability, right? So here's this is the singularity. There's something called the event horizon, okay? And there's something called the Schwarzschild radius. And the radius of that thing is this formula. And we can get this formula two different ways from the IV formulas. The first way is that, of course, we say that this is the kinetic energy. If we fire something up off a surface, and if it has sufficient energy to overcome, remember that this is like negative, right? This potential energy is negative. So really our equation is 1/2 mv squared minus gmm over r, right? If that total energy is 0, then you've achieved escape velocity, if you recall from that chapter, right? So what we do is we set these guys equal. We plug in the speed of light for the escape velocity, right? And we solve for the radius for which the escape velocity is the speed of light, right? So let's do that. So we'll go 1/2 mc squared, right, is g big M, and this is the singularity's mass. Little m, that's your mass, right, over the radius here. And then, of course, we can cancel that. And then I can multiply both sides by 2, divide both sides by c squared, move the r over here, and we end up with r is 2g. This is the mass of the singularity over c squared. So that's one way to do it. They also give you this this velocity equation. This is the orbital velocity equation, right? So if I say c is equal to 2gm over r, imagine that you have to, that's the square root of that, right? Square both sides, so c squared is 2gm over r. Switch these guys, right? R is 2gm over c squared. But anyway, there it is, right? So what this is, of course, 6.67 e minus 11 Newton meters squared, kilograms to the minus 2. This is the mass of the singularity, right? And of course, this is the speed of light. Squared, right? There it is, right? Okay. And then this is the radius of the event horizon, okay? And the event horizon, did I spell horizon right? Is the point, if you are inside here, you cannot escape from the singularity. If you're out here, you can escape, right? And then the final thing I'll leave you with, right, is that if you're a particle just inside the event horizon, remember that your energy can be indeterminate for, or the energy has an uncertainty due to the, right, h over 4 pi, right? Okay, so it's possible to borrow enough energy and mine your way through that barrier. Once you escape, of course, you give the energy back to the vacuum. And this is called Hawking radiation, stuff that escapes from black holes, right? And Stephen Hawking proposed that black holes could lose mass. An isolated black hole, which, turns out it's hard to find those, right? But one that's not getting fed, okay, could sit there and bleed mass that way out of its event horizon just because of the Heisenberg uncertainty principle, right? When the object loses enough mass, it actually unblack holes, right? And that should have a characteristic radiation signature, and we should be able to see that. And we looked for it for years and years and years and never ever saw a black hole coming back into the universe, right? The event horizon going away, right? And Stephen Hawking writes in his book, he says, it's sad that we never found that, because if we had, I would have won the Nobel Prize. All right, so anyway, that's sort of an interesting thing, right? Black holes actually do that by getting smaller. They actually become black holes by getting smaller and smaller and smaller, right? as r gets smaller, the v gets bigger. When v equals c, it becomes a black hole. If you could compact the Earth into about 0.35 of an inch in radius, it would be a black hole. The sun would be, if we could make it a black hole, it would be 1.9 miles in radius. And the sun and the Earth will never, though, in a natural process, become black holes. They could get gobbled up by a black hole, right? All right. So put this is the thing from your note guide, right? What is the maximum radius of a black hole that is 30 million times the mass of the sun? And by the way, we used to think that black holes were these extraordinary exotic things. They are actually quite common. Every galaxy, as far as we can tell, has numerous giant black holes in the center of it, right? So we're going to go, R is 2g mass of the central body over c squared, right? So we're going to go 2 times 6.67 e minus 11 Newton meters squared, right? And then the mass here is 30 million, so 30 E6, right? 30 million solar masses, so 1.99 times 10 to the 30th kilograms, right? And then we're going to divide by the speed of light squared, so 3.00 times 10 to the 8th. And let's square that, and that's meters per second. Hopefully this will end up with radius, right? You know? All right, so 2 times 6.67 e minus 11 times 30 e6 times 1.99 e30 divided by 3e8 squared. Let's see what it is. Oh wow, that's a big number. It's not really being very helpful here. All right, I'm going to have to make it, let's see, mode. Let's go mode. How about scientific notation mode? Good. Okay, clear. Second answer. Now, there we go. I'm getting 8.8488, and then a lot of sixes, right? 6 bar times 10 to the 10th meters, which is, I think that's about a half an astronomical unit, which is interesting. All right. That is the event horizon. So if we replace the sun with a black hole with 30 million stellar masses, right, the event horizon would be about halfway between here and the sun.